Good afternoon. I'm Hugh Dyer, an Associate Director in RSK's Geosciences business. Welcome to the January edition of our 2025 series of Down to Earth webinars. These will cover a broad range of subjects and are available afterwards on our YouTube channel alongside previous talks. Our talk today will begin by Mark Hinsley from our geotechnical team, providing a guide on compaction of soils as engineered fill. But firstly, a brief note on housekeeping during the talk. All attendees' microphones are automatically muted throughout the webinar. During the presentation, you can post questions online and there'll be a Q&A session at the end of the presentation. We will answer as many questions as possible at the end of the talk. Those that can't be answered due to time constraints will be answered after the webinar. Shortly after the webinar, you'll receive a link to a short survey. If you could take a few minutes to provide feedback so that we can improve on future webinars. Now, please let me introduce our speaker today, Mark Hinsley. Mark is an Associate Director in our geotechnical team. Mark has a wide experience in the geotechnical assessment of soils and development of brownfield land for development. He has over 30 years experience in both remediation design and validation and managing complex projects both on-site and office-based. Through his hands-on experience of complex contaminated sites, Mark has detailed knowledge of the practicalities of earthworks design and validation. I'll hand over to Mark now to guide us through the complexities of engineering fill materials.
Right, hello everybody, hopefully you can hear me. I'm having a slight problem at the minute with the technology and the slides are not moving. Oh, yeah, we're back in business. Okay. Well, thank you very much for attending today. What we'll be focusing on today is filling. Basically, we'll be looking at the standard methods of filling that we use today, probably the most widely commonly used, which is basically placing material in thin layers and compacting it with a construction plant to achieve a designed kind of level for our sites and a platform that we can construct on. I won't be covering in the talk, I suppose, more exotic approaches such as dynamic and impact compaction, impact rolling, etc., which really border on ground improvement and probably deserve a separate talk of their own. Nor will I be going on to kind of certain control techniques such as MCV in today's talk, which again probably warrants another talk in its own right. As engineers and developers, we are really happy with sites when we find them. For a variety of reasons, we often want to change site levels, generally to achieve a flatter site and a cut-fill balance. Necessarily, this involves filling to a greater or lesser degree. This fill will need to be at an appropriate standard for its end use, i.e. beneath structures, infrastructure or landscape areas, and the requirements for each of these will vary. First of all, a bit of soil theory. Soil is a mixture. It's not a solid. It's a mixture of soil particles with voids in between them. And these gaps are filled with a mixture of water and air in varying proportions depending upon the soil and how dry it is. When we excavate a soil, we loosen it, we increase these voids, and generally we increase the amount of air within the soil. And as we load soil, it will compress back, reducing the volume and increasing the density. Obviously, we don't want this to happen beneath our structures, as the volume change will cause settlement and if rapid, a bearing failure. So we need to induce it before we build upon it. And we do this by applying a compactive effort. We apply a load on the soil in advance, and this load is a function of the force we apply, which is usually derived from a mass, and and the width of the application that it's applied over. And this compactive effort decreases with depth. And for this reason, we place material in thin layers. However, water can get in the way. Water is incompressible. If we have water within the voids and within the pores, particularly a large amount, it will resist compaction. This is not generally a problem in granular soils where the voids are larger and interconnected, as under the pressure of the load, the water can drain and dissipate. However, in cohesive soils, it's more of a problem because the voids are much smaller, the interconnections are less, it's less permeable, and the water won't dissipate so readily. Cohesive soils then can take a long time to drain, in some cases months to drain. So too much water can be a problem. And controlling the moisture content is one of the most critical elements of compaction. So before we actually start doing any work on our kind of soils and compacting them, we need to understand the soils that we're dealing with. And this is obtained through a series of classification tests. Particle size distributions, which you can see in the top diagram, and which give us an idea of the grading of the soils, the sizes of the particles, from very coarse gravels and boulders down to fine kind of silt particles. And the mixture and combination of these different gradings of soil is important. It tells us whether the soils are uniform, i.e. just one size of particle, or they're well graded, spread over a range of particles. And this will affect the voidage within the soil. We also do Atterberg limit tests, particularly on sample, only really on samples which are cohesive in nature, so basically clays and silts. And this provides information on kind of how they perform. We also want to test the moisture content. As we've already established, that's going to be quite important for our compaction. We'll also look at the optimum moisture content, maximum dry density relationship, which we'll talk about a little later, and also the particle density, which actually determines the density of the individual soil particles, the mineral particles which make up the soil. There's other tests that we may also do dependent on the actual material that we're dealing with. Expansivity, certain slags and so on may expand under certain chemical conditions and when they get wet. Loss and ignition calorific value on certain certain soils like colliery spoil. Is there a risk of an underground fire, sort of like the creation of further voids? Sulfate, concrete attack. We might also have to consider it if we need to modify the moisture by the application of lime, because with certain combinations of sulfate, we can get heave of the soil. We may also need to look at the chemical qualities of the soil to see that it's appropriate for use from a human health point of view as well. So once we've done this, we first of all need to decide, well, can we use the material at all? Is it an unsuitable material? Is it basically a high risk material where we might need to do more work? And you can see here basically quite a large list of unsuitable material taken from both the specification for highway works and the latest NHBC guidance. You'll notice there's some differences between the two guidances that get it in there. And then also what NHBC require with their kind of standards for housing, which they've recently revised at the beginning of last year and are considerably more stringent. So assuming that our material is acceptable, we then need to start looking at the compactive qualities of the material. As we mentioned, too much water resists compaction, but paradoxically, some water is helpful as it greases the particles, it allows them to move over each other and reduces the friction between the soil particles. And for each material or soil, there is as a given compactive effort, there is a sweet spot, a Goldilocks point where you have just the right amount of moisture to grease and allow the particles to move easily, but where it isn't resisting the compaction. And at this point, the optimum moisture content, the greatest density of the soil particles can be achieved. And this greatest density is known as the maximum dry density. When we're compacting soils, we want to get as close to this value as we can. It's really practical to always achieve it, but we usually work to a target of somewhere between 95 to 90% of this value, with 5 to 10% air voids. Now, there's more than one maximum dry density. And the maximum dry density will vary dependent on the material that you're using, as you can see in the diagrams on the left, but it also varies with the amount of compactive effort that you're applying to the soil. Generally, the more compactive effort you're applying, the lower the optimum moisture content will be, and the higher the maximum dry density that you will be able to attain. Typical performance, basically, go back a little bit. There are 3 standard tests that are undertaken with different weights of rammers, which simulate different degrees of compaction. 2.5 kilogram rammer, the lightest, only really for roads and infrastructure. 4.5 kilogram rammer, probably the most commonly used, and then the vibrating hammer, which really only applies to soils with a significant granular content, specialist heavy-duty granular fills. And typically for housing, you'll be working to a target of 95% maximum dry density, 5% air voids with a 4.5 kilogram rammer. Roads and highways, much lower standard, 90% MDD, 10% air voids with a 2.5 kilogram rammer. Now, how we go about achieving this compaction? Well, there's several different methods and approaches which are specified. The first is method compaction. And this really relies on working to a defined method, where you have a given weight of roller, you apply the material in a given thickness, and you apply a number of passes to that weight of roller, to the material, and it's been established from previous experience and monitoring that this will achieve the required degree of compaction that you want. And this approach is taken in probably the most widely used earthwork specification kind of in the UK, which is the Specification for Highway Works, Series 600. But there are a few pitfalls with using the Specification for Highway Works, particularly in relation to building structures on it, because it wasn't designed for that purpose. It was designed for the purpose of building roads. And the target compactions that it was designed to achieve are only 90% maximum dry density and 10% air voids, but with the 2.5 kilogram rammer for general fills. Now, if we're working to building housing, for example, and we're doing it to NHBC standards, that requirement is 95 and 5% air voids at the heavier 4.5 kilogram rammer. So therefore, the methods in the Specification for Highway Works may not deliver the required degree of compaction that you're looking for that end use. However, you can refine the methods in the Specification for Highway Works by undertaking a site-specific trial and doing a comprehensive series of tests on that trial pad to make sure that you're actually achieving the standard with an appropriate method that you need. Obviously, a high degree of classification testing is required with this approach. Strict monitoring of passes and moisture content is required to make sure the method is being delivered. But there's no formal performance or end product testing to demonstrate that you've actually achieved the required standard. You're trusting solely in the method. Unfortunately, most clients, consultants, or regulators are not so trusting, and they'll require some form of testing and proof that you're actually meeting the required standards. And this really relies on undertaking tests during the job to ensure that you're actually either meeting the density requirements that are needed to deliver the performance on the site, or directly measuring the qualities that you're seeking on the site in terms of bearing capacity and settlement. And then also, a further form of a contractual approach is performance, where you're looking at the final performance of the material. You're undertaking tests on the completion of the works using very large, kind of realistic tests which simulate the foundations that you're going to use in future on the site. Obviously, these two approaches potentially require less classification, less monitoring of the actual work itself in terms of passes and so on, but obviously they do have a greater degree of testing as the work goes along and at the end of the project. Now, many specifications are hybrids. They use a combination of all three of these approaches. Method at end to provide confidence that the final performance requirements will be achieved. So how do we assess compaction? Most projects will require some form of end product testing, and there's really two forms of tests: those which assess density and those which assess bearing capacity and settlement. The former, core cutter tests and replacement densities and nuclear and electromagnetic density tests. The latter, various forms of plate bearing tests. And then performance tests, typically done at the end of the job, are much bigger, larger scaled up versions of plate bearing tests, zone tests and skip load tests usually that are applied to the surface of the finished site. And we'll talk a little bit more about these to follow. However, before we can test what density we're actually achieving on site and whether we're meeting the target, we first of all have to define the target that we're working to. And this is obtained from the optimum moisture content maximum dry density curve. And this is a typical curve from a project using a look of it, probably colliery soil on this particular site. In reality, when we're actually setting our target values, we wouldn't just be using one curve, we'd be using a combination of somewhere between 3 and 10 curves to establish our kind of target values. But for clarity, I'm just showing one within this kind of presentation. Now, we'll normally be seeking a target. Let's say this is a residential site, and we're working to the developer is working to the NHBC standards as his warranty body, and we need to hit that target. And that is 95% of the maximum dry density and 5% of the air voids. Now, 95% of the maximum dry density that we're seeing, the MDD on this particular curve is about 1.71, and 95% of this value is 1.64, which is the orange line that we see crossing the diagram. And you can see that it intercepts the axes of the curve at basically between a moisture content of 11.5% and about 19.25%. However, those aren't our kind of moisture content values that we need to work to, because we also need to work to the air voids target. And the air voids are denoted by the green line that you can see crossing and cutting the curve. So to make sure that we hit 5% air voids, the lower moisture content limit needs to be a much higher moisture content, about 14.5%. And so in this case, we'll be working to a maximum dry density of a target of 1.64 or greater, and we'll be looking when we're doing our testing to try and make sure that our soil has a moisture content of between 14.5 and kind of 19, but ideally we're looking really for a target value of around 16 to 17% in the center of that range. If we have moisture contents outside of that range, it's very unlikely we're going to get the right degree of compaction, whatever we do to the soil. So monitoring moisture content during the work is quite important if we're going to hit that, that target and make sure that our material can go down. And that can be achieved, moisture content can be measured in several ways. The most formal one is lab testing. Basically, the material is baked, you weigh it before and you weigh it afterwards, and the difference is the weight of the water. You can also do field testing, which gives you a much quicker result, instantaneous result almost, using moisture meters. The oldest version is still fairly good, is the speedy moisture meter, which uses a desiccant, calcium carbide, and absorb the amount we measure the amount of water that absorbs when it's kind of vigorously kind of shaken with the soil sample. And then there's electronic moisture meters, which measure the kind of resistance of the soil. Neither method is terribly reliable, but it gives you an indication. An alternative approach is to use on-site testing, where effectively you bake the soil on site, again measuring its weight before and after you've baked it. And that can be done either in a microwave or a small oven, kind of a heat lamp. Microwave can be quite quick, but with both of the test methods, you've got to make sure that you prepare the sample quite carefully and that it's actually evenly baked throughout. It can be the case that you can cook and kind of bake some parts of the sample so that it's rock hard, whereas other parts can still retain some moisture. So care does need to be taken when you're sort of taking that approach. But again, you can get a result back on the day and give a yes or no potentially to your material. So they're worth doing. Okay, so when we've measured our moisture content, the material's good to go. We've placed it and put it into the ground. We've rolled a layer. We can now start testing it with kind of field testing equipment. And there's the quickest and cheapest kind of method is using nuclear density and also, I suppose, the new kid on the block, electromagnetic density testing. Both are quick and easy to do, and they work generally by inserting a probe into the ground, in the case of the nuclear density gauge, with a nuclear source at the end of it, and then measuring the signal that comes back to the base plate of the kit. And you can see there the kind of the bar and the sledgehammer that is used to form the hole to insert the probe in, and that with the probe down is actually measuring the signal in the photograph. The electromagnetic density gauge works in a similar method. Two probes inserted into the ground, and then measure the radio frequency waves that ascend between the two and how much are intercepted. Both are quick to do. They're relatively cheap to do, and you can do a large number in a day. And in general cases, you can get certainly uncorrected results back almost immediately. So you've got a good indication of how well your materials performed. The disadvantages with them is that they're less accurate than the more formal sand replacement density and core cutter tests, which I'm going to come to in a minute. And they require regular calibration. Now, the calibration for a nuclear density gauge is quite involved. Usually involves packing a specialist container in the lab and then testing that as a known quantity. A lot of work involved with doing that. Labs don't particularly like doing that form of calibration, or it requires a sand replacement density or core cutter test to be taken at the time that the nuclear density gauge or electromagnetic gauge result is taken. That's sent back to the lab and the results are compared to check that they're within a reasonable tolerance. The problem with that approach, that calibration approach, is that you lose a lot of the advantages of speed with the nuclear density gauge or EMG gauge because of the time that the sand replacement density takes to be tested back at the lab. And what happens when it comes back and it turns out that there's a big difference between it and the NDG results. That can be a bit of an issue, as you may have laid several layers by that time. So the alternative form of tests, which we've already mentioned, the sand replacement density and core cutter tests. These basically involve cutting a circular, sand replacement density involves cutting a circular cylinder in the ground, then excavating the spoil and placing it in the tray that you can see there in the picture, and then filling the hole with a known volume, a known sand of a particular density, a uniform sand. The density and volume of sand used allows you to calculate the volume of the hole, and the soil can then be taken back to the lab, weighed wet, baked, weighed dry, to calculate the density and the dry density of the soil and the moisture content back in the laboratory. Core cutter works in a similar fashion. It just basically involves a metal cylinder being pressed into the soil and then retracted. Obviously, it only works on fairly fine soils, which you can press the core cutter into, and it's got to be retained in the core cutter when you extract it. So generally only really works well on relatively cohesive soils, but quick technique when you can do it. Both of them, core cutter much quicker to actually do on site. The SRD can take up to an hour, but both techniques require lab input, and it can be a few days before you get the result back. And again, with site programs and our desire to get filled down quickly, that can be a problem because we could have another layer or two on the ground by the time we get the result back, in which case it can be a problem if it's not the result that we want. So the alternative approach to actually measuring the density is to actually look at the qualities that we're seeking from the ground directly, bearing capacity and the degree of settlement under the likely loads that we're going to put on the site with our foundations, or with our site infrastructure in respect of the roads. And both the plate bearing test and CVR tests basically involve loading up a plate, a metal plate, an unyielding metal plate with a given load, somewhere between 1.5 and 3 times the actual load that we're going to place on the ground in a series of increments or steps, and seeing how the ground performs underneath the plate, how much settlement and deflection that we get. And you can see a plate bearing test here set up with all the gauges and settlement and deflection gauges set up, and monitoring the ground kind of underneath. The problem with these approaches is that they will only test a limited depth of soil. And this is also an issue with the NDGs and the other tests. They'll only test the individual layer. Plate bearing tests will test maybe 2 or 3 layers, depending upon the size of the plate. Typically, they'll only measure the ground 1.5 times below the diameter of the plate. So if you're using a 600mm PBT plate, you're only going to really be measuring 0.9 meters of the ground beneath it. So you need to allow for that within your design and your specification. You're going to be testing at 0.75 or at most 1 meter intervals with the plate bearing tests. CBRs, again, really not much use because they're so small. They're not only really giving you an indication of the immediate layer beneath the test. Problem with using the larger plates is that because they're larger, to apply the particular bearing pressures you want to, you've got to have a heavier Kent ledge to deliver that pressure and that mass that you're pushing off kind of into the ground. And that usually requires tying up a loaded dumper or an excavator for a couple of hours while you're doing the test. CBR is very quick, but only really useful for roads and services and basically road pavements. PBTs can take a bit rather longer, 1 to 2 hours on site, but again, you can usually get feedback and a result, a provisional result on the day. So now moving on to performance, bearing tests, which is zone and skip tests. And now certainly the NHBC, for those of you who are house builders, have moved basically to definitely requiring end product testing and performance testing at the end of the job for sites that they're involved with. And these really are large scale tests, which usually involve a large plate or concrete foundation, which is specifically cast into the ground, loading it up with a heavy Kent ledge that you can see there. There's a zone test at the bottom, skip tests above, and then undertaking precision leveling on the rods that you can see at the base of the skips and the plate in the zone test at regular intervals, generally over a minimum period of a week, to see how the ground performs and settles under the loads and over an area that you would expect for a typical foundation on the site. So give very good results, very realistic to what you're going to be doing and applying in future. NHBC like them for this kind of reason, but they're expensive. They're expensive to set up, they're time consuming to do. You can only really do them at the end of the job, and you can't rely on them in isolation, because if you haven't done all the previous work and your end product testing, then you may get a failure at the end of the job, in which case you've got a big problem. So yeah. Okay, so what can go wrong with earthworks? Quite a lot, unfortunately. I suppose probably the biggest issue is the fact that you're dealing with soils and that soils are variable. They're not consistent. Even kind of natural soils will vary a bit. That's why you really need to take several up to moisture content maximum dry density tests and use an average to arrive at a target value. But certainly the moisture content can vary with depth and distribution across the site. And I think probably that's the biggest issue with putting kind of material down, is it's either put down too wet or too dry. It's not helped by our climate, and certainly the pressure on clients and so on to work in the winter now. It's quite difficult to keep materials dry, particularly at this time of year. That's exacerbated if you don't control the materials on site properly. You've got to look at stockpiling, sealing your stockpiles. If a material is dry enough to place, keeping it dry enough to place. Once you've placed it, making sure that it stays of a reasonable quality, designing your filling so that you've got a slight crossfall so that the water will drain off your placed material and it's not softened by the weather. You also have to be mindful of the variability of the maximum dry density and material changes during the work. It's particularly crucial with kind of, I suppose, man-made materials in terms of pulverized fuel ash, colliery spoil, and so on. That can vary quite a lot, and visually it appears the same. So you need to be undertaking optimum moisture content and maximum dry density tests throughout the works, just to check that your kind of target values and so on are kind of are accurate and the material hasn't changed. It's no good actually just doing them at the beginning of the job and then working to that target, because that target may become outdated through a change of material during the life of the job. Another problem with the practicality of earthworks is sometimes unrealistic expectations. If you've got a site which is really wet and the natural moisture content of the soil is really wet, and you're expecting to get a high degree of compaction out of it, well, you're going to have a problem. You're either going to have to modify the moisture, perhaps using lime, to kind of basically extract some of the moisture from the soil, or which costs quite a good deal of money, or you're going to have to settle for a lower degree of compaction and perhaps some other solution to your foundation problem, perhaps piling or deep trench foundations through the fill and then compact it to a lower standard. So sometimes, yes, you can struggle to make a silk purse out of a sow's ear. Presence of obstructions, really you need to be breaking out obstructions, trying to work around them and compact properly around them is a nightmare. It's very difficult to get heavyweight compaction plan which can work in small areas, and that again goes for awkward geometries as well. Side slopes you often need to tie into kind of natural material, and those need to be kind of benched, and you need to cut appropriate benches to suit, usually a minimum angle of 1 in 2, and your bench should be really the height of your layer that you're placing, and then 2 times the width. Timing of testing and coordination of testing is also very important. So obviously you want to get your lab in as soon as possible after you've placed a layer to do your maybe your NDGs or your EMGs. They may not be available. You can receive lab results often kind of days and weeks after you want them, which can lead to kind of work being undertaken at risk. And then, yeah, we've already mentioned the issues with calibration equipment, and you need to make sure that your plant is suitable for the work, meets the appropriate standards that you're going to need for, say, compacting that layer, particularly if you're using method compaction as a basis. So, faced with all these problems and the limitations of the testing and so on, well, what can we do to make sure that we achieve a successful project and satisfy all the regulators and get our houses or our shed or roads built? Well, the first thing really, in any project really, is thorough site investigation. You need to have a good definition of material types that you're likely to be reusing, understand the distribution of those materials on the site, and sufficient testing to be able to generate our target values and so on for use within the works. And that may mean in doing additional testing at the beginning of the site works, and then also further testing during the earthworks. We need to plan the earthworks appropriately. And we need to have a kind of realistic earthworks design, which takes into account the limitations of the materials, the use that you're proposing, and it needs to fit in with the foundation solution. And the two need to work hand in hand. And it may be that your ultimate sort of foundation solution is a combination of earthworks, ground improvement, and specialist foundation design. And it needs to be a realistic program. There's many sites where you're working on sites which are clays and so on. It's not a good idea to start them in the middle of winter. The traditional earthwork system, the season was sort of St. Patrick's Day, middle of March, for a pretty good reason, in that the weather improves thereafter and the ground will dry out. A good initial compaction trial with all materials is kind of very important, although generally you won't be working to a purely method compaction approach. The method spec in the specification of the highway works is a good basis to start from. And by sort of modifying that and coming up with a definite method to work to, you're improving your chances of hitting your end product and performance targets at the end of the job. Mentioned about the need to kind of manage the site properly so that we keep our materials dry and we preserve the quality of the fill that we've placed. But we also need to have thorough supervision, either internally, if a contractor, or if you've got independent supervision, such as ourselves on site, looking at the works, in terms of actively managing the moisture on site, undertaking tests on the moisture content to make sure that the material is going down at the right moisture content, keeping on top and checking the classification is what it should be, and making sure that everything is properly calibrated, and monitoring the results, and very importantly, interpreting the results in real time. Basically looking at the results and interpreting them as soon as we get them back. Don't let them drift for 2 or 3 weeks, because you may then go back, look at the results and find, well, actually, oh no, we had a problem with that layer. There's a bit of an anomalous result there. We're getting loads of very low kind of readings, but that layer is now actually 3 or 4 layers down. It then becomes very expensive to do any remedial work on it. In addition, the supervisor should be another pair of eyes, and there's a lot still to be said, but actually just physically and visually observing the work and watching the material as it goes down, and seeing how it performs beneath the roller. Are you getting a bow wave? Does it seem to be bouncing? Because if both of those things are happening, you've got a clear problem. So yeah, it's not easy, particularly to the kind of more stringent standards, which certainly are now applying for house building and house builders with the NHBC's revised chapter 4.6. But with good control, it can be done. And that brings us to a close. I'll be looking forward, perhaps is the wrong word, to some questions now.
Right, thank you, Mark. That was very interesting insight into engineered fill. We have a few questions coming in, so please, if you do have questions, submit them to the questions. The first one, you mentioned undertaking testing during the compaction work. Is there a set or recommended frequency for testing to be undertaken?
Well, that's a good question. It sort of depends. It depends on the site. It depends on the materials. I think generally with nuclear density gauges, and electromagnetic gauges. Probably be working on either a 25-meter grid for your layer, or maybe a slightly tighter grid, 20-meter grid. So probably between kind of 1 per 100 cubic meters, 150 cubic meters. They're the quick, cheap and cheerful tests to do. Sand replacement densities, you'd probably be doing at least one a day to calibrate your nuclear density gauges, or with one kind of visit. Optimal moisture content, maximum dry density tests. That depends on the volume that you're dealing with. I would say that you would want to do a minimum of 3 tests to properly generate your target value, regardless of the volume of material that you're using, and then probably take a test at 1 to 1,000 cubic meters afterwards. Classification tests, similar. You may want to take the test more or less frequently, and maybe reduce that down to 1 in 500 cubic meters if you think the material kind of is variable. There is guidance given in BS 6031, BS for earthworks, on testing frequencies, but it will depend on the site, the variability of material, and the information that you already have from the SI.
Right. Okay, that's very useful. Another question: when you talk about supervision, does this need to be full-time or can it be part-time supervision? And what are the advantages of full-time supervision?
Well, again, it sort of depends upon your kind of end use of the site and the particular requirements of your client and the regulator involved. Certainly now, NHBC are putting more stress on supervision, and they're putting on more stress on kind of full-time and independent supervision. So, within their revised 4.6, they sort of mention that, if you've only got loose control, loose supervision on the site, then they will require a more onerous form of foundation than if you've got high degree of control, high degree of testing, and so on. There is like a graded kind of foundation solution. They'll require more effort actually put into the foundation because they haven't got the same confidence in the control that's being exercised on site. I'm not a fan of part-time supervision, basically because of what happens when you're not there, and the fact that the unscrupulous ground workers and contractors, the minute your back's turned, they'll be doing things they know they shouldn't be, and then picking up on them can be difficult when you kind of return to site. Also, a lot of kind of particularly in relation to earthworks, needs really a timely response, and actually responding as quickly as possible to a problem, because program is usually all you're seeking to capitalize on good weather and get the material down as fast as you can. You've got quite a lot of delays built into the system anyway, with getting some results back from the lab, and then usually have to go to the contractor, then to you, and so on. And it can be 2 or 3 days before a problem is identified, and then the quicker you can identify it, the smaller the problem will be if you have to do some remedial action and maybe dig that material out. It's a lot more complicated if it's now buried under 3, 4, or even 5 kind of new layers of good material. You then become very unpopular.
I'm conscious of time, so I think we'll just do 1 or 2 more questions. The NHBC guidance that you mentioned, people have asked whether this relates to just the development plots, so the foundation construction, or whether it relates to the estate roads and estate road construction as well, whether one's under the specification for highway works and one's under the NHBC.
The NHBC have become much more stringent within their chapter 4.6 kind of filling. They certainly require 95 and 5, 4.5 gram rammer beneath structures. It's a little bit confusing within the chapter as to exactly what they require underneath infrastructure, but it's certainly implied that they need 95 and 5 to 2.5 kilogram rammer in those areas. In other areas of the site, say where you may have attenuation ponds or kind of landscaping and so on, then you're welcome to work to a method, compaction, or to a kind of 90-10 or whatever. And they do have a little diagram in the chapter 4.6.3, which sort of shows different scenarios in which different specification requirements sort of can be given. And in terms of filling beneath the structures as well, that quality of fill has to apply to the full zone of the foundation. So generally at a minimum angle of 45 degrees down from the sort of development footprint.
Right, fantastic. Thank you, Mark. I think we'll end the questions there, and the further questions that we've had in will be answered by Mark once he's had a chance to review these. So thank you very much to Mark. Our next Down to Earth talk will be on Tuesday, the 11th of February, and we'll look at understanding gas protection measures and the requirements for validation. Please remember to complete the feedback following the presentation. And thank you very much for attending today, and we'll see you again in February.